Example 1, find the integral of x cubed plus x over x minus 1 dx. Sidebar, x cubed plus x divided by x minus 1 is demonstrated. Back to the text. Solution. Since the degree of the numerator is greater than the degree of the denominator, we first perform the long division. This enables us to write the integral of x cubed plus x divided by x minus 1 dx equals the integral of open x squared plus x plus 2 plus 2 over x minus 1 close dx equals x cubed over 3 plus x squared over 2 plus 2x plus 2 the natural log of the absolute value of x minus 1 plus big C. In the case of an equation 1 whose denominator is more complicated, the next step is to factor the denominator big Q of x as far as possible. It can be shown that any polynomial big Q can be factored as a product of linear factors of the form ax plus b and irreducible quadratic factors of the form ax squared plus bx plus c, where b squared minus 4ac is less than 0. For instance, if big Q of x equals x to the 4th power minus 16, we could factor it as big Q of x equals open x squared minus 4 close open x squared plus 4 close equals open x minus 2 close open x plus 2 close open x squared plus 4 close. The third step is to express the proper rational function big R of x over big Q of x from equation 1 as a sum of partial fractions of the form big A over open ax plus b close to the power I, or a big A x plus big B over open ax squared plus bx plus c close to the power j. A theorem in algebra guarantees that it is always possible to do this. We explain the details for the 4 cases that occur. Case 1, the denominator big Q of x is a product of distinct linear factors. This means that we can write big Q of x equals open a sub 1 x plus b sub 1 close open a sub 2 x plus b sub 2 close ellipsis open a sub k x plus b sub k close, where no factor is repeated and no factor is a constant multiple of another. In this case, the partial fraction theorem states that there exist constants big A sub 1, big A sub 2, and big A sub k, such that equation 2, big R of x over big Q of x equals big A sub 1 over A sub 1 x plus b sub 1 plus big A sub 2 over A sub 2 x plus b sub 2 plus ellipses plus big A sub k over A sub k x plus b sub k. These constants can be determined as in the following example. Example 2. Evaluate the integral x squared plus 2x minus 1 over 2x cubed plus 3x squared minus 2x. Solution. Since the degree of the numerator is less than the degree of the denominator, we don't need to divide. We factor the denominator as 2x cubed plus 3x squared minus 2x equals x open 2x squared plus 3x minus 2 close equals x open 2x minus 1 close open x plus 2 close. Since the denominator has three distinct linear factors, the partial fraction decomposition of the integrand 2 has the form equation 3, x squared plus 2x minus 1 over x open 2x minus 1 close open x plus 2 close equals big A over x plus big B over 2x minus 1 plus big C over x plus 2. Sidebar. Another method for finding big A, big B, and big C is given in the note after this example. Good. Back to the text. To determine the values of big A, big B, big C, we multiply both sides of this equation by the product of the denominators. X open 2x minus 1 close open x plus 2 close. Obtaining equation 4, x squared plus 2x minus 1 equals big A open 2x minus 1 close open 2x plus 2 close plus big B x open x plus 2 close plus big C x open 2x minus 1 close. Expanding the right side of equation 4 and writing it in the standard form for polynomials, we get equation 5 x squared plus 2x minus 1 equals open 2 big A plus big B plus 2 big C close x squared plus open 3 big A plus 2 big B minus big C close x minus 2 big A. The polynomials in equation 5 are identical, so their coefficients must be equal. The coefficient of x squared on the right side, 2 big A plus big B plus 2 big C, must equal the coefficient of x squared on the left side, namely 1. Likewise, the coefficients of x are equal and the constant terms are equal. This gives the following system of equations for capitals A, B, and C. 2 big A plus big B plus 2 big C equals 1. 3 big A plus 2 big B minus C equals 2. Negative 2 big A equals negative 1. Solving, we get big A equals 1/2, big B equals 1/5, and big C equals negative 1/10. And so we have a sidebar. We could check our work by taking the terms to a common denominator and adding them. Figure 4 shows the graphs of the integrand in example 2, and it's indefinite integral with big K equals 0. Which is which? Back to the text. The integral of x squared plus 2x minus 1 over 2x cubed plus 3x squared minus 2x dx equals the integral of open 1/2 1 over x plus 1 over 5 1 over 2x minus 1 minus 1 over 10 1 over x plus 2 close dx equals 1/2 the natural log of x plus 1/10 the natural log of 2 I'm restarting that line, equals the natural log of the absolute value of x plus 1/10 the natural log of the absolute value of 2x minus 1 minus 1/10 the natural log of the absolute value of x plus 2 plus big K. And integrating the middle term, we have made the mental substitution u equals 2x minus 1, which gives du equals 2 dx, and dx equals 1/2 du. Note, we can use an alternative method to find the coefficients, capitals A, B, and C, in example 2. Equation 4 is an identity. It is true for every value of x. Let's choose values of x that simplify the equation. If we put x equals 0 in equation 4, then the third terms on the right side vanish, and the equation becomes negative 2 big A equals negative 1, or big A equals 1/2. Likewise, x equals 1/2 gives 5 big B over 4 equals 1/4, and x equals negative 2 gives 10 big C equals negative 1. So big B equals 1 over 5, and big C equals negative 1 over 10. You may object that equation 3 is not valid for x equals 0, 1/2, or negative 2. So why should equation 4 be valid for those values? In fact, equation 4 is true for all values of x, even x equals 0, 1/2, and negative 2. See exercise 73 for the reason